Okay, good day everyone. So what I want to discuss in this video are missing values, which are kind of without a doubt a common hurdle in statistical analyses. And values can be missing for any number of reasons. So maybe a participant never showed up for a research session, maybe a lab animal died, maybe there was an equipment malfunction, maybe someone recorded something incorrectly, or who knows, maybe you just ran out of time and money. All these things are possibilities that are frequently encountered in research, and they result in missing values appearing in your data sets. So, for this reason, the R language actually has a specific way of denoting missing values. It simply uses the abbreviation NA, which just stands for not available. And in most cases, any numerical calculations that you make on an NA value will simply result in another NA value being produced. So as an example, suppose we type something like 5 plus NA, and we run that, you can see we just get an output of NA. And intuitively, this behavior should make a fair amount of sense, right? If you think about it, we don't know what the missing value is in this case. So the expression 5 plus NA just simply cannot be evaluated. And R quite logically extends this principle to its functions. So for instance, if you have, say, a vector of values, so let's say X here, and suppose we have the values 1, 2, 3, 4, and 5. And let's just pretend 4 here is a missing value. If you try and calculate the mean of x here, just using R's standard function for the mean by typing something like mean of x and running that, you can see it outputs a missing value. So you can see that we're not able to calculate the mean here. But why can't we? We clearly, if you look, we have enough numbers to theoretically calculate a mean. Why doesn't R just ignore this missing value? Well, the reason is that the way in which missing values should be handled is actually a matter of pretty great importance, and statisticians often disagree on what the best practice should be in any given case. Now, it has to be said that in a situation like this, what we should realistically do here is pretty obvious, right? We can just straightforwardly ignore the missing element and treat the vector x here as containing only 4 values. But there are many scenarios for which that is not the best course of action, and it's really to R's credit that it doesn't automatically do this. R wants you, the user, to decide how missing values get handled because, depending on the context in which this function is being used, that could be a very important decision. Furthermore, you may not even realize that you have missing values in your data, and having R output a value of NA clues you into that fact pretty clearly or pretty quickly. The reality is most data sets are not this simplistic. There are many situations where you should not be ignoring the missing value. So, for instance, in a more complex scenario, this missing value might be statistically paired with another observation of a different variable that you've also collected in your research. That's a situation where you might, for the purpose of conducting a certain type of analysis, require a number to be in this fourth spot. But you don't have that number, right? So what do you do then? Do you replace the missing value with the mean of the 4 values? Do you replace it with the median, or do you do something else entirely? There's no one size fits all answer here. However, in those instances where simply ignoring the missing value is the sensible course of action, many standard R functions do allow you to specify an additional argument called na.rm that will remove any missing values prior to running the calculation. And you can see this by just simply accessing the help documentation. So if we access the help documentation for the mean here, what you can see is the function has this argument na.rm. And you can see it defaults to false here. But if we set that to true, then that will strip the missing value prior to the computation. So if we do this, we just say na.rm and we set that to true, you can see it calculates the mean of 1, 2, 3, and 5, and you get a value of 2.75. But what about situations where a function doesn't have an na removal argument? Well, for those situations, we can use a special function called is.na to help us. So what this function does is it evaluates whether each element of an R object is missing or not, and just simply returns a logical true or false value. So for example, if we insert x into our function here and we run that, you can see we get just false, 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 true, false. So we can tell from this output that the fourth value is a missing value because it returned a true. In other words, the function here has determined that the fourth value is an NA value. Now, what's interesting is if we put a negation sign in front of this, and in R, a negation sign is just denoted with an exclamation mark. If we put that there and we run this, you can see that now the output shows the opposite set of values. So you notice we get true, 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 false, true. So the fourth value is now false and everything else is true. Basically, this negation sign that we've included here means that the function is now evaluating whether each element of our vector is not a missing value. Thus, if something is not missing, it will return true, and if it is missing, it will return false. And you might ask yourself, well, what use is that? Well, this is useful because we can combine this set of logical values that we've just kind of produced here with the indexing feature of vectors that we learned about, and we can easily exclude the missing value. So, for instance, if we type x and we use our indexing brackets, we put our negation sign and we say is.na, and then we insert x and we run that, you can see it gives us our original vector, but it's excluded that missing value. In other words, the indexing has returned only those values which got evaluated as true. So kind of putting all of this together, what we could do is we could write mean and just insert that, run it, and you can see we get 2.75. Now, if you're a novice R user, a strategy like this probably seems a bit cumbersome, particularly when you're working with so few values and it's very easy to see kind of what is and isn't missing within your data. So for instance, instead of using indexing to remove the values here, what we could have done instead is just created an entirely new vector, right? We could have just said 1, 2, 3, and 5. Run that, calculate our mean, like so, right? Very simple. The problem with this method, though, is that most data sets are too large to kind of eyeball and manually rebuild in this way. Oftentimes you're working with data sets of hundreds, if not thousands of values, and you might have just a few missing values that are kind of scattered about in random spots. Consequently, we really do need automated solutions, kind of like this indexing solution we have here, because not only are they going to save time, but they're going to be less prone to error as well. Now, one more function that it can be handy to know about in the context of missing values is the which function. So recall that is.na tells us which values are missing using true and false statements. Right, so let's just redo that. So we can see that the fourth value here returns as true, indicating that it is in fact a missing value. But to determine that it's the fourth value in this case, we kind of need to count where this true is falling within our vector, right? We have to kind of go 1, 2, 3, 4. And, doing something like that is kind of time consuming, it's inconvenient, it's prone to error, particularly when you have large data sets. So what we can do instead is we can have R explicitly tell us where that true value is located using the which function. So this is a function that quite literally tells us which indices are true, hence its name. In other words, it gives you the index value of the true elements in your vector. So if we say is.na, we just say x, and you run that, you can see it spits out a 4. So that is where the missing value is located in our vector. And we can even verify this, right? So we can just use our indexing, put in a 4, run that, and you can see it spits out an NA. And this function works even if you have more than one missing value. So if we create a vector y here, let's just say y is 10, NA, 20, 30, 40, 50, NA, like that. Run that, and we'll redo this process. So we'll say which, right, is.na, insert y, run that, and you can see it tells us 2 and 7 are where the NA values are located. So what we could do now is we could actually store this little vector of values here and tell our index to ignore them with just a minus sign. So we could store our missing values. We could just store them as an object called missing, right? So now if we run missing, you can see it just spits out 2 and 7. And now what we can do is we can type y, get our indexing brackets, insert missing. And if we run that, you can see it just spits out the 2 NA values. But recall what we learned when we talked about atomic vectors. We just put a little minus sign right there. You can see it shows us everything that isn't a missing value now. So we get 10, 20, 30, 40, and 50. Pretty straightforward. An alternative method that you could have employed here is to literally just insert this like so and put the little minus sign. And that works too. But this method is usually the preferable method because by having your missing values stored as an object, you can kind of easily call them up when you need to and look at them and see explicitly which values are missing.